Okay, perfect. So as you can see on the screen, so I've completed the placement for you, and it was the assignment, the last assignment that I gave you on the day 10. So you can use this board for the reference if you do the placement by your own. So that is what I mentioned. So completed the assignment number 7 by following placement. So here you can see I just followed the placement planning, whatever the section where we want to place all the sections, whatever we have planned, I've just executed all the sections. And this is our PMIC, this is LPDDR4. Here we have type C for programming and debugging. Here we have type C for power up this SOM. Apart from that, we have eMMC and Ethernet fee in this section. And this section we have all the regulators and buck converters, LDOs. Here we have Wi-Fi module and their connectors, right? And at the middle we have system on chip. So after that, so what I did, if I'll show you on the folder. So today I'm going to share this folder with you, and here you can see 2 zip files. So one is the latest library of the system on module project. Apart from that, you'll see another file. So that file is SOM board with RK3399 with SOM placement. So here I've completed the assignment number 7, and you can find that that zip file inside the folder, whatever I'm going to share today. Okay, so today our most important things that we're going to do today is the fan out of all these components, whatever the components at the middle of the system on chip. We're going to fan out those, and to fan out those components we have to define few design rules, and those design rules will be for the VIA at the beginning, and some thick tracks that we're going to use for to connect between the pad of RK3399 and the pads of capacitors. Those will be like as much as thick as possible. We'll try to make them thick, but because of space constraint, we have to just follow the design rule. Apart from that, another thing that we have to complete is we'll prepare the impedance profile. So if you know, we are using lot of high speed tracks, right? Some are the differentials, some are the single ended tracks, right? So we're going to define, or we're going to prepare the impedance profile on the layer stack manager. After that, another step is, so after defining the impedance profile, we have to create the rule, right? And like for what we define the impedance profile? We define impedance profiles if we are dealing with single-ended tracks. So that impedance profile will be basically the width of the track, right? But if we are dealing with differential track, so those design rules will be for the width as well as the gap between the positive and negative part of that, right? So we're going to define those for all the high-speed connections, right? So this will be the plan for today's session, and we'll end after completing those things. We'll end today's session. In next session, so again, today and the next session is very, very important, and yeah, the next to next session is also important. So on the next session, we will basically do the design rules for routing the high-speed nets. Okay, so on those we have to fan out the LPDDR4 RAMs. Why I'm telling you this? Because I just want you to look into those and see if you wanna read about those, what should be the clearance, everything. And again, we have that our impedance document, the Excel sheet that we're going to follow. On that, I've noted down each and every design rule that we have to implement on LTM Designer. So next thing will be the layout planning. Okay, so after defining the design rules, we'll plan the layout. Okay, on which layer we're going to route what section of the high-speed tracks. Okay, we'll do that on Paint as always. Apart from that, another thing is the layout. Again, layout planning we have already did. Apart from that, we have to find out the STRAM byte. So again, we'll target byte group. Okay, like for example, we have 4 byte group for the SDRAM1. So there we'll basically target each byte group one by one, and by following a simple procedure, we're going to just make the connections between the SDRAM and SOC. And then we have to just complete every high speed routing. So on the next session, we will complete each and every high speed track. And yeah, that is the plan. So let's start with this one. So here, before starting something, I just want to note down few things here, whatever the design rules I'm going to follow. So in case if you want, you can just use it for other designs as well. So the first thing is via. So I'm just going to note down what are the via properties I'm going to follow. So on via, we have to just put two dimensions. One is the hole and its diameter, right? So let's talk about via hole. Okay, and another is its diameter. So the rule is the via hole at least or the diameter of a via should be at least twice as the via hole. Okay, this is the minimum, or maybe you people heard about that aspect ratio, right? So that aspect ratio is this thing, and it also depends on the height of via, like what is the PCB height, or if you are using some you can say blind vias or buried vias, you have to follow that formula. Okay, so you can just Google that and read about it, what is that. So in our case, we're going to use 0.1 mm and the diameter will be 0.27 mm. Okay, another thing, before implementing those via properties or via dimensions, you have to verify that from the manufacturers as well. So these are the few points you have to just take care of. First is aspect ratio as per manufacturer. Okay, apart from that, you have to verify the either the vias are manufacturable or not. Okay, now, so this is the thing. Okay, so you can simply ask why I am using this size of via. I mean, I can use 0.2 mm or 0.4 mm via. Also I can use 0.4, 0.8 mm vias. Why I'm using 0.1 mm and 0.27, and the reason behind it, behind this thing, is the pitch between the pads of RK3399. So if you'll see, the pitch is very small, which is almost 0.6 mm, right? So the whole gap is 0.6 mm. Okay, and if you see it diagonally, because we're going to place most of the vias in this section, so it is not too much, right? It is 0.9 mm. Like, you can just round figure, you can take it like 1 mm. So we have a gap between these two pads, or the diagonal pads. It's 1 mm, right? So at least go for the clearance. Clearance should be minimum 0.1 mm if you're going to route multiple power vias and power nets on this section. For example, you can take anyone, right? For example, this one, right? So here we have these GPU and VDD logics are together, right? And the gap between those is just 1 mm approx, right? So if I'm going to place a very big via on this one, you will see the problem with the clearance constraint, right? So yeah, during the placement, or during the machine soldering or something like that, this clearance is again not enough, right? So for that, we're going to use as a small via as possible, and obviously it should be manufacturable, otherwise no point to use those. So again, I just figured out, because see, my plan is I'm going to use 6 mil clearance between the via and the pad. So if we'll talk about clearance, I'm going to use, it should be minimum 6 mil, or you can just target 0.1 mm at least between via and the pad. Okay, and with this clearance, whatever the size of via you can able to design, you have to design those. Okay, so let's start with that. Yeah, so that is one thing. And how we decide the track width. So I'm talking about, let's suppose I've placed a via in this section, okay, and I have to connect that via with this VDD GPU pin. Okay, so for that we have to just place a track between those, right? So that track can be 0.1 mm thick, 0.2 mm thick, 0.05 mm thick. Okay. So how to decide the thickness of that track? So again, we're going to route a power track, right? Or the power net here, right? Between the via and the pad. So ideally, what should be the dimension of those, or you can say the width of that track, as thick as possible, right? Because we're going to route the power track. And if you can see, so if suppose we are using very thin track for power tracks or something like that, so there will be then parasitics will be involved, right? The impedance, or you can say, right, the resistance of that track will include, the impedance of the track will include on that. So that's why we target, okay, as thick as possible. Now you can see what size of via we're going to use here. We're going to use, let's suppose, so I'm just noting down that as well. So let's suppose we're going to use 0.27 mm the diameter of via. Okay, so that means if I'm going to increase the width of that track between the pad and via greater than 0.27, it will be again the clearance issue. You're getting my point? Because then that track will be, let's suppose if I route those, I don't think, okay, so we have to put the design rules, but I hope you got my point. I can draw that on paint so you can visualize it. So let's suppose this is our pad, okay, and here we have few more pads. Okay, now we have to place a via. So I placed a via at the middle of this one as we decided. Okay, now its thickness, its track thickness can be, anything. I'll route those. So my point is the track thickness will be as much as the width of, or you can say the outer diameter of the via. If we'll increase that track thickness greater than the outer diameter, you'll see again there will be clearance issues, right? Because this point will be, this clearance will decrease, this clearance will decrease, right? So to maintain the clearance, whatever we have planned, which is like at least 0.1 mm, we have to just route the track width as a size of the outer diameter of via. Okay, I hope you got my point. So that is one thing. So let's implement those things and start routing these connections. Okay, so firstly go to the design rules and go to the routing via styles, and here you have to just implement those dimensions. So the minimum outer diameter I'm going to use is 0.2 mm. The maximum it can go, let's suppose 0.8 mm for PMICs and whatever the high current carrying tracks. We're going to place a lot of vias there for stitching. Apart from that, preferred, let's go for 0.27 mm. Similarly here, so this is the via hole size. Let's go for minimum 0.1 mm. Maximum it can go up to 0.4 mm for the bigger through hole vias that we're going to use on power planes or some polygon ports or something like that. And preferred, let's go for 0.1 mm. Okay, and apply. So this is just half part. Another part is we have to define the track width as well. So for that, go to the width, and here we have to define what is the minimum width you want. So let's suppose I want a minimum 3 mil. Again, you have to just check it with the manufacturers. Maximum you can go for let's suppose 1 mm, and preferred is 0.27 mm. Okay, and apply this as well. That's it.
Yeah,
let's check for DRC. Yeah, tell me.
So is there any calculator we can use to calculate the accurate track width, just to be sure if we are designing for the right current, let's say for a power track?
So here what we're going to do at the end, so this is just we are routing all the connections, so we can kind of see what are the space left. So at the end we're going to fill we're going to use the the polygon pore on the top and bottom layer for all these same nets. Okay, and after that we're going to place multiple vias on that. But at the beginning, we just want to make a minimum connection between those, so we can verify, okay, this thing is enough, right? We just find out everything. Okay, so I would recommend at the beginning, like, don't think too much, like don't think about the carrying current or anything like that. But after the fan out of whole BGA, what we're going to do, as I told you, we'll just place a very thick connection or very thick power, the polygon pore on this one, and there we can place bigger vias or something like that. So we can see there, okay, like we have you can just same nets together, or those number of vias are can able to carry that amount of current or not. You got my point? So at the beginning, just follow this procedure so you can able to fan out. Got it? Okay.
Yep, thank you.
So this is one thing. Now the next step is, so again, as I told you at the beginning when we started the placement, we're going to redo the placement again, and you can see at this time we just we didn't know, okay, where we're going to place via and where we have to place all the capacitors as well, right? Or is the clearance is enough or not between those. So here we just place these components so we can able to kind of visualize where we can spread all the components. So for example, as I told you on the last session, we can spread the component on this section here, right, like that, and then we can route a little bit bigger track to make those connections. So now the next step is we have to just select all these components and place them outside the board, and then start their placement again. But at that time we'll start with the fan out. Okay, so for that, just press Shift S, so you can move to the single layer mode, and from there select the bottom layer. The next step is just select all those components whatever under the SOC. Just select these as well. Okay, now drag those components outside the board. Okay, now go back to again multi-layer mode. Okay, so now we can start with the placement again, but this time we'll start with the routing. So the next thing is, now when we were doing the placement of the bypass capacitors, how do we know, okay, where we have to place the VCC pad of the capacitor or where should be the ground? So you can see in this section, let's suppose for VDD GPU, you'll see each pad for power net is kind of next to the ground, right? So using that, you have to visualize, okay, what should be the orientation of the capacitor that you're going to place. For example, we have these 4 vias. Okay, for these 4 vias, what should be the orientation of the capacitors? Okay, so here one the capacitor's power pad will be this side and the ground pad will be this side. Okay, let me snip this one so I can draw. Okay, so again, how we have to place the capacitor. So I'm just going to use the blue pen. Okay, and I don't know how to make it thicker. Okay, anyways, so let's suppose, so one capacitor will be this one, another capacitor will be this one. Okay, there is no point to place the capacitors. So this is the ground pad of the capacitor and this is the power pad of the capacitor. So there is no point to place it like at 180-degree rotation, right? Similarly for this one. So here you have to just visualize how things should be connected and how we have to start the component placement. Okay, so the next step is we have to place the via. So just drag a via, press tab, just check the dimension of that. So okay, before that just press Q so you can see the metric dimensions, and place the via again, tab. Okay, just check the dimensions. So hole size is 0.1 mm, diameter is 0.27. okay, so you have to place that via at the center of this one. Okay, or you can say the approx center. Okay, so here we forgot to change the clearance rule. So again, go to the design rules, and as we decided, we'll start with the 0.1 mm clearance. Okay. Perfect. So again, I'm just going to assign the same net so you can visualize it properly like this. Now we're going to route a connection. So press tab, hold on. Okay, so again press tab and change the width of this one. So we're going to start with 0.27, which is the exact outer diameter of the via, like this. Okay, and this will be our template for each and every connections that we're going to use, or you can say the fan out of all the power nets. So I'll just copy that and paste it somewhere here. So whenever required, I have to just drag the cursor and just we can directly copy and paste from there. So again here just select those, Control X, and just remove it. Hold on. Now tell me, so again, how I should start the fan out, either this way or this way or this way or this way. Okay, so again, if I'll do like this one, hold on. Okay, if I'll go like this, so again one will be like this, another will be like this, and you can see the area that the capacitor will going to take is too much, right? So here we have to place a lot of other components, but if we'll see at the other side, if I'll place the component like this and like this, so you can see my ground will be connected in this section. So here we can place either ground in this way and it will be directly connected on the ground pad, because the component will be at the bottom layer, right? So I hope you're getting my point. So I always prefer just put some extra connections like this, because again we know that we are using a lot of extra capacitors, and during the placement we will realize that, because the number of pads are less, I guess, for this one, for the little CPU connections. So here we have like less number of pads, only 6 pairs, but the capacitors we have too much. So on that case, we'll realize, okay, the number of capacitors are 2 or 3 capacitors are more than the required one. So we're going to remove those, because there is no point to pack everything and just so that can impact the other fan outs as well, because here we have all the byte groups. Here we have all the high speed tracks of type C, HDMI, PCI on this section. Okay, so if all those capacitors will be like so much spread, there will be like power tracks will be routed there, so it will be difficult for us to expose or fan out from these tracks, from these pads. Okay, so there is no point to place a lot of component. So let's start with this one, like this. So firstly, I'm just going to highlight those. Okay, the next step is select this. So I'm just going to remove this one, select this, Control C, and place them quickly. Okay, so these are those V-shapes connection. Now the problem with these connections are there is one more problem. So I hope you can able to visualize that. So there is a term that we use generally, the through hole VRs and the internal planes. So here, we are using a 12 layer stack up. We have some internal power planes or grounds that we're going to connect. So here you can see this dark green part, that is the clearance between the plane, the copper and the via, and this is huge, right? And if you'll visualize that on 3D mode, select any layer, Shift S, select any plane, and you can see this whole section. If I'm going to use the ground, this whole section, all the ground will be removed, right? So again, whatever the tracks will going to route here, their return path or their coupling with the ground is like completely removed for those, right? Because of that clearance. So the solution for that is, again, that much clearance is not required here. And LTM, just when you create the new project, it is the default clearance, that is I guess it is 20 mil, which is not required. So we're going to use like around 8 mil or 7 mil as per our requirement. So again, how I've decided that what should be the clearance. So you can just imagine, right? Like as per your past experience or whatever the board you have designed, what should be the clearance between a pad and the ground, right? It should be minimum of 10 mil or 8 mil, something like that. Sometimes we can go for the 6 mil as well if required. So there is not any kind of hard and fast rule. Okay, you have to follow that clearance only. This is just a power net and a ground, right? So you have to think like that. So for that, what you have to do, you have to go to the design, rules, and you have to go to the plane section, and under plane, I guess, no, not this one. Yeah, this is the one. So you can see, if I'll convert that into the mil, press Q again. So it is 20 mil by default, right? So let's go for 8 mil, and if you'll see required, we can just decrease that further. And after that, you can see it is reduced. And again, if you'll go for the 3D mode, you can see now we have ground which is completely filled between those, right? So there is a ground under the track. That is one thing. Now just save the project. Now we can go for the capacitor placement.